This lesson is about conditional distributions of jointly distributed random variables. So the first thing that we should do is remember the conditional probability for events A and B, and that was defined like this. The probability of A given B is the probability of A and B divided by the probability of B. And the idea there, and that's going to be important, is that you restrict yourself. So if you have events A and B, then you restrict yourself to event B, right? If you're given B, then you know B has occurred, and then you are looking at A within B. So A and B, the portion of A within B, right? This portion here, that is part of the whole of B. So that is the definition for events. Now, that definition is going to come into play when we start talking about jointly distributed conditional distributions. So we're going to look at an example first and then give the definition. So let's suppose that x and y are jointly distributed discrete random variables with PMF given here, P of x, y, as in this table. So we can find the marginal distributions, and you remember if you add up the columns, given that we have y situated like this, then that is giving us the marginal distribution of y, and if you add up the rows, that is giving you the marginal distribution of x. So p sub x of x and p sub y of y. Now, suppose that we were looking for a conditional distribution, conditional probability. We'll get to the distribution in just a second. Imagine that we wanted the probability that x equals 2 given that y equals 3. Well, what would we do? We'd apply the definition of conditional probability, and that's the probability that x equals 2 and y equals 3 divided by the probability that y equals 3. That's exactly the definition that we had for events. Now, if we look at what that means in the table, however, well, the probability that y equals 3, well, that was y equals 3 here. That means you're concentrating on the column of y equals 3. And the probability that x is equal to 2 within that column is this. So you're restricting yourself to the probability that y equals 3. Incidentally, the probability that y equals 3 is given to us by the marginal, right? That's exactly what we did. We added up that column, and that's the probability that y equals 3. The probability that x equals 2 and y equals 3, well, that's exactly what this table gives us, right? That is the PMF at 2, 3. And so that 0.09 is the numerator over the marginal value is the denominator. And so we get that probability as 1/3, And there's no reason that we could do that only for sort of one x value. We could continue and do for all the x values, right? We just did x equals 2. Well, if we did x equals 1 and 3, then we're taking up all the x values here. And so we could do the exact same thing. The probability that x equals 1 given y equals 3, well, that turns out to be the probability of 1, right? So the probability of 1, 3, the first entry here, over the same probability of the column, right? The same marginal of y. And that gives us 5/27. And then we can do the same thing for x equals 3. So that's the probability of 3, 3, right? So that's in purple here. That is the numerator, the probability, the joint PMF, P of 3, 3, over the marginal PMF. Again, this entry over the column entry. And so that gives us 13/27. So we've looked at all the x values. In other words, we have just created a new distribution for those x values, but they have been restricted. They've been restricted to where y equals 3. And so that distribution is called the conditional distribution for x given y equals 3, because all of our calculations were given y equals 3. And so there is our new PMF. There is a PMF, a single variable probability mass function for our x values, 1, 2, and 3. And the notation here, the probability of x, the probability mass function, x given y equals 3 of x given y equals 3, right? So this is a random variable x, and these are the little values x that our random variable can take. So that is what is behind this definition, the definition of a conditional distribution. So let x and y be jointly distributed discrete random variables with joint PMF P of xy. Then the conditional distribution for x, given that y is equal to y, has probability mass function P of x given that y equals y of little x given that y equals y. That is a heavy notation, and not all books use that notation, but it is important, I think, to get all of the details down, and so we are going to be a little heavy and cumbersome in our notation. This is one of the standard ones, and it is the most explicit, and we are going to use that one. But we have to remember, right, in all of our notations, capital letters signify the random variables, small letters signify values that those random variables can take. So is the joint PMF, P of xy, over the marginal P sub y of xy. And that is over the appropriate support, and that is going to be very important. We're going to take a look at that, especially in the continuous case in just a moment. And so as we said here, the denominator is the marginal. The denominator here, P sub y of y, is the marginal mass function for y. And so, of course, there's nothing special about x. We could define P sub y given x equals x of y given x equals x as the same thing, except now you're dividing by the marginal of x. So comment here, these conditional distributions, right, once you have them, they're just like this table here. It's just like any single variable distribution, discrete distribution. Once you have them, you can find probabilities, conditional probabilities, you can find expected values, etc., just like you would do with any discrete distribution. So if we continue with our example, if we have the same PMF as above, now let's find the mass function the other way around. Let's find the probability P sub y given that x equals 2 of y given x equals 2. And then let's use that to calculate a probability, the probability that y is greater than or equal to 3 given x equals 2, an expected value, a conditional expected value, the expected value of y given x equals 2, and a conditional variance. So let's go ahead and do all of that. So if we're looking here, this is the new distribution mass function that we want. So that is the probability P sub y given x equals 2. Well, x equals 2 is this row here, right? And so we're going to restrict ourselves to this row, and we are looking at each of those values, each of these values here divided by the total, right? So we're looking at, to apply this rule right here, so we're looking at the P of xy divided by P sub x of, well, x equals 2. And so if we do that and we create our new distribution for y, we get this table here, right? 0.07 over 0.34 gives me 7 over 34. 0.08 over 0.34, 8 over 34, and etc., right? So there is our conditional distribution, the distribution of y given that x equals 2. Now that we have this distribution, well, there is nothing unusual about it. We do all the calculations exactly as we normally would. You want the probability that y is greater than 3, greater than or equal to 3 given x equals 2. Well, this part is it's no longer important. We've taken care of it. I mean, it's important. We no longer need to pay special care to it because we've already done that. It's incorporated in this PMF. So what do? Well, we just use the PMF like we normally would. The probability that y is greater than or equal to 3 in the conditional distribution is just probability of 3 and probability of 4, so we add them together. The same thing for the expected value. Given y is equal to 2, no, given x is equal to 2, the expected value of y given x equals 2, same thing. We have already incorporated the fact. We've taken care of the fact that x equals 2, and so we just calculate the expected value using this distribution as if it were any old probability mass function, right? And so we are doing the sum of the y times the p of y all the way along, and you do that, and you get this value, right? We're doing the sum over all of the y values given x equals 2 of y times the probability of y given x equals 2, right? So we're doing exactly as you normally would for expected value. Same thing for variance. You want variance, well, you need e of y squared given x equals 2 minus e of y given x equals 2. So y squared calculated the same way, right? You're calculating the square of the y values times the probability of those y values given x equals 2. You crunch through that number and you get the value there. So this, once you have that distribution, once you have that conditional distribution, it is treated like any other distribution. So let's go and look in the continuous case, which we will do in the next video.